recording. Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 6, Comparative Studies, Cross-sectional, naturalistic, or multinomial sampling, Section 6.8, Attributable Risk. We are working through the same example with maternal age and the birth weight of babies. And A is the maternal age being less than or equal to 20 years. Not being an A is having a maternal age greater than 20. Birth weight B is having a baby that's less than approximately 5.51 pounds. And not B is having a baby who weighs more than about 2,500 grams or about 5.51 pounds. So we're working through our same data set. We're setting up the tables, the joint proportions, the joint frequencies, and so on. We are calculating our critical value for our Z. And then we are going to calculate some probabilities. So we can calculate the probability of B given A. So that's the probability of having a low birth weight baby, given that the mother is less than or equal to 20 years old, and that's 20%. We can calculate the probability of B given not A, and the probability of not B given A, as well as the probability of not B given not A. We can look at the marginal probabilities, being P of A, P of not B, P of A, P of not A, P of B, P of not B. Now, if we want to calculate the relative risk, that is given in equation 6.94 of the text. That's the probability of B given A divided by the probability of B given not A. And the relative risk in this case is equal to 2. Now, we can use the relative risk to calculate the attributable risk, also known as the etological fraction or the population attributable risk. And if this risk factor could be eliminated, the attributable risk can be defined as the proportion by which the prevalence, the rate of occurrence of the outcome characteristic in the population would be reduced. And make sure that you really read through the text in this chapter because it gives some great information about just about all the context around attributable risk and relative risk. So we can use equation 6.93 to get the attributable risk. Here, I'm taking the last line of that equation to calculate the attributable risk, 20%. And what that means is that if we could take out the risk factor of being a young mother, we would reduce the risk of low birth weight babies by about 20%. Now, in reality, we cannot get rid of that risk factor. There are going to be women who have babies when they are younger. And so take that with a grain of salt and be careful when you're explaining attributable risk. The different forms of equation 6.93 can be found in each of those lines. And I just wanted to give you examples to show that it really wouldn't have mattered which form you used. These are all equivalent forms that are given in the text. And no matter which one you use, you get the same value of 20%. All right, so now we can look at the attributable risk among the exposed, and that's given in equation 6.95 of the text. You can calculate that. That's 0.5. Another way to calculate it, another way to think about it is 1 minus 1 over the relative risk. So we get 0.5 no matter what. So what does the attributable risk among the exposed give you? This gives you a measure of the excess risk as a fraction of the risk among those exposed to the antecedent factor. All right, so we have examples in our text of how to interpret attributable risk among the exposed, but just note that the attributable risk among the exposed does not depend at all on the prevalence of the exposure of A. It does not indicate the impact of the exposure among the wider group of all those who have the disease in the population, as does the attributable risk, RA. So for etological research, the attributable risk is more important. But there's just different ways of expressing risk for different situations, and that's what you're going to want to take into account. All right. Alternative forms of equation 6.93 are given in equation 6.96. Here they are. P of A given B is not defined. Let's make sure that we've defined everything. All right, if you have an established P of A given B, you're going to want to enter that in. So if you look at P of A given B, that's going to be your first proportion divided by the column total proportion. So once we read in P of A given B, then this form should work for 6.97, and we still get the value of 0.2. Now, really important topics is that 6.97, so this alternative form of expressing the population attributable risk fraction, this shows that the population attributable risk is equal to the attributable risk among the exposed, reduced by the prevalence of the antecedent factor among those with the disease. In method 1 sampling, each of the required rates or conditional probabilities can be estimated. So you can use either form. I want you to think about that for a minute. All right, in fact, there's another important advantage that's discussed in the text. So really give page 127, especially a read, but the whole chapter, of course. The interpretation of the attributable risk is the proportion by which the probability of B would be reduced if the risk factor A could be eliminated. This is an oversimplification and idealization of actual experience in public health practice. So you have to keep in mind that there's usually confounding factors that correlate with both the exposure and disease, and it wouldn't disappear even if we could have the exposure eliminated. And in this case, it's impossible to have the exposure eliminated. And in other cases, it's impossible. But even when it is possible, I think that because of this confounding, you would never see it completely go away. And that's what the book's trying to get at. All right. So what we can do is we can move on to table 6.10 in the text. And this is giving us a specific example of infant mortality by birth weight. So we're now no longer talking about the birth weight of babies and the maternal age. Now we're talking about, given the particular birth weights, how many of those babies survive or not. Okay, so looking at this table, we can set up the overall sample size of 72,730 births. And we can set out the proportions that are given in the table. So when we do this, we can look at table 6.10 and get those proportions. And from here, we can see that for babies who are above 5.51 pounds approximately, about 92% of them survive, right? And in the horrible case where a baby does not survive, that's happening in about 1% of births, regardless of the birth weight, right? And then also this 6%, that's great progress for health and medicine, where we have babies who do have low birth weight and they end up surviving, okay? So we can look at all of these marginal proportions, make sure to save them. And then we can get an estimate of the attributable risk. This is in expressions 6.10 through 6.105 of our text, right? So the estimated risk of infant death attributable to low birth weight is 0.563. We can get the standard error of that estimate. And then we can work on getting the confidence interval. And one way we do this, because we want to make sure that the risk is on the correct scale, is first we're going to take the natural log of 1 minus the attributable risk. And then what we're going to do is we're going to do a back transformation to get it back on the odds ratio scale. And this will guarantee that our attributable risk is not going out of the domain of risk. So we get our confidence interval for the natural log first, right? And then we're going to exponentiate those values and subtract that from 1. We're doing our back transformation. And we get the limits for our 95% confidence interval for the attributable risk to be between 0.53 and 0.594. So essentially what we're saying here is that we are 95% confident that between 53% and 59% of all of the infant deaths that we saw in New York City in 1974 could have been prevented if low birth weight could be eliminated. So if we could guarantee that all the births of these babies were bigger than 5.51 pounds, then we can reduce infant mortality. Thank you, and I apologize for such a serious topic in our textbook, but this is what people are interested in studying so that we can improve outcomes for all people.